Okay, sir.
Yeah. Okay. So thank you, Urna and Anupam, for the invitation. It's a pleasure to be back to ICTS, as usual. So originally, I was supposed to talk about this topic here, which is the universal survival probability for a d-dimensional run-and-tumble particle, which is the main topic of this conference, the so-called RTP. And this was actually a recent work jointly done with my graduate student, Francisco Muri, who is working with myself and Gregory at Orsay, and also in collaboration with Pierre Ledusal at École Normale. And this was just published in last week's PRL. But before I get to this topic, so since I have 2 lectures now, so what I'll do is, I'll just give a very general introduction to this so-called first passage probability, or persistence, or sometimes survival probability for generic stochastic processes. So this is a field which has been around for many, many years, starting from Paul Levy in mathematics literature. And in physics literature, there was a lot of work by, a beautiful article by Chandrasekhar in 1943 Review of Modern Physics. This is really a fantastic article. It has many, many applications of first passage properties in astrophysics context. And there are, of course, many other books like Feller, 2 volumes. And Redner, Sid Redner has a nice book on first passage processes. But all these 3 references, and there are many others, of course, which are mostly for Markov processes, and I'll define what is Markov and what is a non-Markov process. And then in the 90s and early 2000s, there was a lot of activity in the sort of non-equilibrium physics community on these problems of persistence and first passage properties in out-of-equilibrium systems. And so I cannot review everything, but these are mostly non-Markovian processes. And here's a review that we wrote with Alan Bray and Gregory Sher, and which is, so if you are interested, you can have a look in this review article. And my talk mostly today will be some glimpses from this review article, essentially. And also there's a Leuven lectures that I gave some years back. And so this is, the lecture notes are published in Physica A that you can also find. Okay. So what is the survival probability or persistence, or the related first passage probability? So as I said, this is a topic which is widely studied in physics, of course, chemistry, biology, computer science, and mathematics. And there's, sort of many different applications of this problem. So the simplest, way to think about this first, it came about going back to the time of Smoluchowski, which is in chemical reactions. So imagine that you have 2 molecules which are diffusing around A and B in space. And when they meet, at some point they will meet for the first time. And when they meet, they react to make something, let's say some C. So A plus B goes to C. Okay. So the time for the formation of C, so which is the sort of production rate for C, so that is essentially related to the time at which they first meet. So this is the first passage time. That means when is the first time these 2 particles are going to meet each other. Okay, so it's a stochastic, it's a random variable because it depends on the actual dynamics, history of evolution of these processes, and also the initial positions and many other quantities. And so one would like to know what is the distribution of the time, or the mean first passage time, and which is the mean reaction time for the formation of C. So that is how actually it was originally studied in the chemistry lecture quite a bit. Then of course, it has a lot of applications in search processes, in computer science as well as in ecology and other problems. So imagine that an animal is searching for a food. So you have some food here, and the animal is just doing some stochastic motion, which could be just random walk, or any other some complicated stochastic process. And so the process stops when basically the searcher, it finds the food. Okay, so the first time you reach the target, so that's the first passage time. Okay, and again it's a random variable because the actual evolution, the trajectory is random. trajectory is stochastic, and so one would like to know the time when you reach the target for the first time. And this is not just the target searching for food, animal searching for food, but you can think of a computer algorithm. You have a complicated landscape, and you have a computer, randomized algorithm, which is trying to find the local minimum of the complicated landscape. So something like that. Let's say you are looking for the global minimum of this energy minimum, and so you do some kind of stochastic motion on this landscape, and the first time you find the local minimum, so the process stops, and that's the first passage time also. Okay, so there's a lot of problem in the computer science. Then of course in finance, I mean, you can think of the stochastic process, which is the price of a stock. So x of tau versus tau, and okay, it's doing some random motion like this. So stock is going up, and then some strange event like coronavirus happens, it falls, and so on. And so you can, there is a very natural question that when is the first time the stock, hits some level? This can be any arbitrary level, x0. So when is the first time it goes below the level x0? Okay, so this is this time here. So this is the first passage time, tau f. First time it hits a certain level. Okay, so in finance it's a very important object to study. Similarly, in insurance risk processes, and many other things. And then I mentioned astrophysics. So just one example, and this goes back to someone who is one of my favorite scientists, is James Hammersley. This is the same Hammersley who actually discovered with broadband percolation theory, and he was a sort of mathematician or physicist, if you like, in Oxford, and he always did things 10 years ahead of the field. Okay, so the famous Edwards-Wilkinson's model of fluctuating interfaces that we talk about, which was 1981, Hammersley actually did it in 1965, 15 years before, and in a beautiful article. And this guy was always ahead of his field. Okay, so 10 years ahead. So he's known for percolation theory and other mathematical processes, but he actually did many great things. So Hammersley was interested in the escape of a comet from the solar system. Okay, so here's the problem. So let's say you have the sun, very roughly speaking, schematic picture. So you have these, different planets which are going around, and there's a big planet which is Jupiter somewhere. So what happens when a comet comes into the solar system? Comet means basically a comet is like a Halley's comet, which is just a collection of dust particles, if you like, matter, something like this. I have some picture. I can show you maybe later. So the comet basically comes into the solar system with some negative energy, okay? And then it gets stuck into and moves around in the orbit. So if you plot the energy of the comet in the ith orbit, so it makes the orbit, okay? So initially it comes with some negative energy. So let's call it minus E0. Then each time it comes around the orbit, but what happens, because it's a very sort of soft object in some sense, when it comes very close to, during the orbital motion, when it comes very close to a bigger planet like Jupiter, so Jupiter attracts some mass from the comet, so it loses some mass, it loses some energy, and sometimes it can gain also some energy from gathering more particles and more kinetic energy. So what happens is that the energy, so if you measure the energy after each orbit, it's never fixed, it's never constant. So this is orbit initially, and then after one period, after 2 period, after 3 period, you measure, it's not just a flat number, it doesn't remain fixed. It fluctuates from one orbit to another orbit, okay? So if you look at the data, you will see something like this. So it goes up, and this is because when it comes closer to Jupiter and things like that, then it comes down, then maybe goes up, and so on. At some point, in some after n n period of orbit, maybe its energy actually becomes positive. Okay? So when its energy becomes positive, there is no binding energy, it just escapes from the solar system. So the lifetime of the comet, which is the number of periods it stays in this solar system, is exactly the first time this process crosses the origin and becomes positive, for example. Okay? So this is the context in which, so the energy itself is doing a kind of stochastic motion here. And Hammersley actually studied, with the real data. He was trying to model this lifetime of the comet and so on. Okay? So you can find a little bit of discussion in that in Chandrasekhar's article. So this is the general context. So we have, so the general question is, so consider any sort of generic stochastic process. So right now I don't specify this process. So this process, if you do any particular realization of the process, maybe it starts from some initial value and it's doing something, some random motion. Okay. And I observe the process up to some fixed time t. This is my time axis. This could be price of a stock. So first I'll define the survival probability. So this is I'll denote by S of t x naught. Sometimes it's denoted by S x naught t. So this is, by definition, this is the probability that starting at x naught, and suppose the x naught is positive initially, the process does not cross some level, let's say 0 for simplicity, up to time t. So it's a function of t and x naught, starting position. So this is the generic question you can ask, and this is the, and first passage probability is related to it. So this is a probability density. So t is the random variable here. So ft x naught dt. So this is the probability that the process starting at x naught crosses the origin or any other level for that matter for the first time in the time interval t to t plus dt. Okay, so this is the probability density and this is the probability when you multiply it by dt. So why are the two related? Very easy, because if I want to calculate the survival probability up to time t, so think of this picture. So you don't know what happened after that. So this means that the first passage event has not yet happened up to time t, okay? Which means that the first passage event happens after time t. So this is simply f tau x naught d tau t to infinity. Okay? Because imagine that you let the trajectory go, at some point it will cross, but that crossing, so you are looking at the event where this process did not cross the origin up to time t, okay? Which means that it must have crossed after time t, if at all it crossed. So this is the simple relation, which means if I take a derivative with respect to time, okay, so f of t x naught, just taking derivative with respect to time, is just minus del s del t. So sometimes people talk in terms of first passage probability, sometimes survival probability or persistence. So this is also sometimes called persistence. Persistence with the process, the probability for the process to persist on one side of the origin. Okay. So this is a sort of object that this object, is a very general question for any arbitrary stochastic processes. Okay. So now I'll define. So in general, these are very hard. If you give me the dynamics, if you give me the stochastic process, the probability distribution of the trajectory, it's not always easy to compute this object. Okay, and people have tried many things. In very few processes for which you can actually compute this survival probability. And one of the type of processes for which you can compute this is these are so-called Markov processes. So what is a Markov process? So Markov processes are processes without any memory. And I'll tell you what I mean by that. So simplest example of this is just random walk or Brownian motion. Let's say Brownian motion. Let's say one-dimensional Brownian motion, or Wiener process. So what is a Brownian motion? Everybody knows. So dx d tau is just a white noise. Okay. So this noise, expectation value of the noise, so it's a Gaussian white noise. So it's a Gaussian noise whose mean is 0. And for Gaussian process, I just need to specify just the 2-point correlator. And the 2-point correlator is just 2d times delta function of tau minus tau. Okay. So which means the noise is totally uncorrelated in time. Okay. So then you see that this is, you can think of this as a discretized process like tau plus d tau is x of tau plus eta tau d tau. Okay. So which means that if I look at this process here, at some point x naught is doing something like this, because each time you are hitting the process with the noise, and the increment is just IID random variables. So each time is going up and down like a random walk. Okay, this is just a continuous time version of random walk. And then, so the point about this process when eta has a delta function correlation, so which means that if I want to know the position of the particle at time t plus d tau, all I need to know, because this is a first order equation, all I need to know is just the position at the previous time step and the local noise in time. Okay? I don't need to know the history, previous history. If you tell me, okay, the particle was here at time tau, and you tell me what is the kick, what is the noise at that time, so then I'm totally, fully able to specify the process. It doesn't remember what happened before that. If you specify the current position and current noise, that's it. That specifies the process full trajectory. Okay? So such processes where it doesn't depend on the previous history, so these are called Markov processes. And typically, if you have a noise which is a delta correlator, and if you have a first order equation here, then that's a Markov process. Okay? So an example of a non-Markov process, simplest example. So you just take the second derivative here. It's a random acceleration instead of random velocity. So again, eta tau, you can take it to be a white noise, delta function correlated. But the point is now you have a second derivative here. So if I discretize, so tau plus d tau minus 2 x of tau plus x of tau minus d tau equal to eta tau d tau. So if I want to specify the position of the particle at time tau plus d tau, I need to know x of tau, the previous time step, as well as x of tau minus d tau. So 2 steps. So it's a Markov process which is a 2-step Markov process, okay, and the local noise. So if you tell me the local noise and the 2 previous positions, then I'm able to specify the trajectory. So it goes back in history a little bit, but not too much. Okay. So this is the simplest example of a non-Markov process, and So even though, for example, for these processes, okay, for this guy, we'll see in a minute, you can calculate, of course, the calculation of the position distribution at time t for both processes is very simple because these are just Gaussian processes. So the answer will be just Gaussian, basically, with a given variance. But to calculate the survival probability, while this is easy, first passage, and we'll do it in a minute, this problem, just this problem, to calculate just this object, S of t x naught, for this problem, it took 50 years to solve. So it was first suggested, actually, in a paper by Wang and Uhlenbeck. Yep. Yes, good question. I'll come to that. So I'll just tell you. So and that explains why. So see, again, what Spenta is saying is that this is a random acceleration problem, but I can go to the phase space, right? I can write down this as dx dt equal to v and dv dt equal to noise. Okay? Now, so in this xv plane, of course, it's a Markov process because there's a first order thing. Problem is, to solve the survival probability, you have to write down in this 2D xv plane the Fokker-Planck equation, which with the absorbing boundary, and that's a technically very hard problem even for this simple problem. And it took 50 years to solve this. Okay? So it was suggested by Wang and Uhlenbeck in a very nice review of modern physics, 1945. So I suggest everybody to read this, or have a look at least in the RMP. This is just after the war, and I've never seen a single RMP with so many Nobel laureates in it. Okay, everybody, from Pauli to Feynman, everybody wrote articles in this. It was just a peace conciliation effort after the war. But each article is a gem, really, fantastic. So anyway, so it was suggested, but they realized that this problem is not very well defined, because you see what happened here. Okay, I'm straying a little bit, but it's good to say. So for this, okay, before that, maybe I should first do this just to show you how to compute the survival probability for simple Brownian motion, and then I'll just maybe talk about this a little bit later. So let's start with the, just 1D Brownian motion. This dx d tau equal to eta of t, and you want to compute the survival probability up to time t, right? So this is our process. So I want that the particle doesn't cross the origin up to time t. So there are many ways to solve this problem. So there's one which is just by solving what is called the forward Fokker-Planck equation. Then there's a backward Fokker-Planck equation, and then there's a path integral method. Okay? I will not go through all these different details. You can find this. I wrote a very pedagogical article in Current Science in 2005. This is in Spenta's book on the Einstein Brownian functions. You remember that. So anyway, so let me just show you at least one. So let's look at the forward Fokker-Planck equation. So what does it mean? So I want to know the trajectories. So let's say that the final position that the particle reaches is at x. Okay? So I want to calculate the probability that the particle reaches x, is just a propagator, probability particle reaches at x, starting at x naught in time t, probability density. Okay? So if I know this object, and then I have to integrate over the final position, because the final position, the path can arrive anywhere here, any positive value. You don't care, because you want to sum up all possibilities that it stays positive. Okay? So when you integrate over the final position, this is your ST of x naught. So to compute this, if I know this, I can just do the integral and compute this. Now, what is this object does? So this is very easy because it's just, again, a Markov process. So you can write down the Fokker-Planck equation for this, where x belongs to the upper half, 0 to infinity. X has to be positive, right, because it cannot cross the origin. So you have a partial differential equation with this in this domain. I have to specify the boundary and initial condition. So the boundary conditions are so one boundary condition is that the p at x equal to 0 at any time t for any x naught should be equal to 0. So this is what is called the absorbing boundary condition, because you don't want any trajectory which crosses the origin and before reaching t, right? So if you insist that the p is 0 at the x equal to 0, then that actually cuts off all the trajectories that crosses the origin, okay? So you just put a Dirichlet boundary condition at x equal to 0. And of course, the other boundary condition that when x goes to infinity, so the probability that you will, in a finite time t, if you starting at x naught, the probability that you will reach at infinity is essentially 0. Okay? And the initial condition is that p at x at t equal to 0 is just delta function of x minus x naught. Okay? So it's just a simple Green's function problem, and it's like electrostatic problem. So we can solve by the method of images. I'll just write down the solution. So there's a unique solution of this problem, and we'll see what I mean by image method. So you can check that this satisfies the boundary condition, because if I put x equal to 0, it's 0 by construction. If I put x goes to infinity, it goes to 0. It satisfies the initial condition, because when you take t equal to 0, this guy becomes delta function of x minus x naught, and this is delta function of x plus x naught. But since your x is between 0 to infinity, this condition is never satisfied. So therefore, this is a unique solution. And how do we arrive at this solution? Because very simple. Because you see, this is, imagine that you don't have this constraint here. Okay? So then the free space Green's function is just the diffusion Green's function, which is like this. And to make this boundary condition at x equal to 0, satisfying absorbing boundary condition, what I can do is I can imagine that there's an image here sitting at minus x naught, and I look at all the paths that come from x naught to x, just like in electrostatics. And I put a negative sign here so that when at x equal to 0, they exactly cancel each other. So this is exactly how you solve the Laplace's equation by image method if you want to find out the potential due to some charges. So with some conductor at v equal to, so potential satisfied del square phi equal to whatever minus charge times delta functions. And then you put, if you put a conductor here, the v is 0. And to satisfy that, you just put an image charge, and then you just take a linear combination of that. Okay? So you can do it you can find it, this is very natural things, okay? So once you have the image solution, then you just integrate this object, just substitute it and integrate, and you'll get just error function of x naught over square root of 4 dt. D is the diffusion constant, and the error function is defined as 2 over root pi 0 to z e to the power minus u square du. So in particular, what you notice is that if you keep x naught fixed and take a large time limit at very late time, so this is just using this, because error function for small argument goes like 2 over root pi times z. So this guy just goes like 2 over root pi x naught over square root of 4 dt. So basically it decays as a power law as t to the power half, as theta, or this exponent theta is half. So consequently, the first passage probability, which is just the derivative of this guy, so this guy decays like very slowly as a power law for late times, and with an exponent which is 3 by 2. And this is the classic 3 by 2 exponent, which was derived by Levy in maths literature, and then later by Chandrasekhar for the Monte Brownian motion. Okay, so you see it's relatively simple. So this is the forward Fokker-Planck. Alternatively, you could work with backward Fokker-Planck, where you don't look at the final position at all. You just vary the initial position, and so if you can write down a direct differential equation for S of t x naught, which is again a diffusion equation. So, but now you treat the x naught initial position as a variable, and then it's easy to show that this satisfies this equation with the boundary condition that at x naught equal to 0, so this is for x naught positive, x naught equal to 0, it should be 0, because if you start at x naught, and if you start at the origin, then you will cross the origin infinitely often immediately, so you won't survive for any finite time t. So again, you have a sort of absorbing boundary condition. And then you have the other boundary condition when x naught goes to infinity. This should be 1, because if you start at infinity very far away, then you will definitely survive up to some finite time t. And you have the initial condition, which is that this is 1 for all x naught strictly positive. Because at 0 time, you are definitely going to survive unless you are sitting at the origin. Okay? So with these three conditions, you can solve this partial differential equation. You can just take a Laplace transform with respect to this, and you will get exactly arrive at this answer. Okay, I'm not showing you this. So the advantage of the backward sometimes is that you don't have to do this extra integration step over the final position. Okay? So backwards are often useful for solving this kind of survival probability of first passage problems. Okay, so this is for this simple 1D Brownian motion. So now, if you come to this random acceleration process, you can write down this, you can follow the same procedure as above. You first make it a Markov process, okay? Because otherwise you cannot write down a partial differential equation directly in terms of x, because it's a second order equation. So you have to do it in the phase space. So you have to define this generator P of x v t starting at, let's say initially at x naught 0, okay, x naught and some v naught and 0. But with the condition that you should not cross the origin. So this is a restricted Green's function basically. And so the equation for Fokker-Planck equation for this guy will be, you can check, I mean this will be not, this is easy to derive. This is a forward Fokker-Planck equation. Okay, so this is in the xv plane. Now, the question is, so you are looking at x positive, right? Because you don't want the particle to cross the origin at x equal to 0. So what are the boundary conditions? So, and this is where the history behind this problem is. Wang and Lindbeck, they were not very sure what is the boundary condition. So it turns out that the boundary condition here is that at x equal to 0 for any arbitrary v at time t is 0 only for v positive. Okay? So that means on this semi-infinite axis, the p goes to 0. This is the right boundary condition. If you look at the microscopic trajectories, and if you want the particle not to cross the origin, this is the right boundary condition. It took some time to understand this, but okay, now you can understand. Just just discretize this equation and try to write down the equation, the boundary condition. Then you will see that this is exactly the correct boundary condition. Okay. So the problem, the mathematical problem was that this problem is well defined. I have a partial differential equation. I give you a boundary condition only on the semi-infinite plane. I mean, does it have a unique solution? Okay, it was not clear in the beginning. So people tried a lot, and finally, a sort of very good progress was made by two mathematicians called Marshall and Watson from Manchester in 1985. So they wrote a paper. The title of the paper is "A Drop of Ink Falls from My Pen, I Know Not When." Okay. And so what they proved is that there exists a unique set of eigenfunctions, a complete set, which actually does satisfy the boundary conditions, and therefore any solution you can expand as a linear combination of these eigenfunctions. So there exists a complete set. But even with that, to compute the survival probability was very hard. Okay? And finally, in 1993, so two people solved this problem. So one was Sinai, the famous Sinai. He solved a discrete version of the problem. And then Ted Burkhardt, who solved a continuum version of the problem using these eigenfunctions, more or less simultaneously. Yes? Why these boundary conditions? Because you see that here, okay, it's a little bit difficult to explain in the forward. If you write down the back, you can write down this equation in the backward equation. So if you say P, the backward generator would be, similarly, sorry. Something like that. So the point is that, if you are at, so imagine that this is the x equal to 0, right? So at the origin, you can have a trajectory at the origin with a, if you start there with a positive velocity, you can still survive. But if you start with a negative velocity, you'll immediately cross, right? So there's a difference between positive and negative velocity. Okay. So in the forward equation, I mean, if you look at this, so you don't want a trajectory to be there, with a positive velocity. That means it must have been on the negative side at some previous time, which is forbidden, right? So that's the reason. So mathematically, the problem was to find the explicit solution to this. And so these guys solved it. And in fact, the answer is, okay, answer is very complicated in terms of Airy functions and so on, but the late time decay was again a power law with an exponent which is 1/4. It's highly non-trivial. Okay. So the first passage will go like 1/t⁵/4. And this is already you can see that the moment you make non-Markovian, it becomes extremely non-trivial, right? So here is a set of open problems for anybody who is interested. So now imagine that I consider this problem here. Where n is an integer, it can be any integer. So n equal to 1 is Brownian motion. N equal to 2 is this random acceleration problem. So it turns out there are physical relations for higher values of n. Okay, so n equal to 3. So these appear in the fluctuating interfaces problem. Okay, so I'm not going into the details of that. But for example, n equal to 3. Again, you can go into the x, v1, v2 plane and make it Markov. But if I ask what is the survival probability, so numerically it's known that it decays as a power law. Nobody knows what the exponent is. It's still an open problem. Okay, so numerically it's about 0.23, etc. So if you increase the value of n, what you can show is that in the limit n goes to infinity, it actually approaches a constant, and this constant is 0.1875. Okay, this has been, okay, there's a lot of history. I mean, you can look at this in our review article on this problem. Okay? So this is just to illustrate that the non-Markov processes, the persistence or survival probability is a non-trivial problem. And there are thousands of open problems which are difficult to solve, but very interesting problems. So what I'll do today, as I mentioned, this since this is a conference on active particles, so I will talk about another non-Markovian process, which is this RTP, run-and-tumble particle. And there we'll see some result which is, I mean, to me it was a shocking result actually. So it was totally hyper-universality. And this is what I want to tell you in the next few minutes. So this is the run-and-tumble particle. You must have heard a lot of talks about it in this workshop. So and the important point in my talk will be the sort of universality of it, and I'll tell you exactly what I mean by that. So the model that I want to talk about is this RTP, run-and-tumble particle. So in the recent literature on active particle systems, these have been extensively studied, where you have many different, many particle system, RTP with interactions and so on. And so extensive studies in recent years. These are interacting many-body systems, and there have been very nice collective properties. So these people are mostly interested in the collective effects. So I'm not writing down the names because there are too many, and you have already heard many talks. So for example, this clustering at the boundaries, then jamming. Yeah, I'll define what the model is. I have not defined. Yeah, I'll make a precise definition for you. Okay, so just wait. So non-Boltzmann distribution. Motility, blah, 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 jamming, and so on. So these are all very nice properties that people have studied. But the point is that even a single RTP, and again I have not defined RTP yet, even a single particle, okay, that is non-interacting RTP or a single particle, single RTP, I mean, with a sort of finite persistence time. So this also exhibits, so without even explicit interaction, just a single particle, it exhibits many interesting properties. Okay, and this has been studied quite a bit in recent literature, I mean, including many people in this room. So I'll not go into all these things. But the point is that this RTP, actually this active system literature, somehow they completely ignored the history of this problem. So this problem was first introduced, this RTP problem. It goes back to somebody called R. Furth in 1920. Okay. And then later, Mark Katz actually gave a beautiful set of lectures in Schlumberger in front of the oil industry people. Okay. Because he was just telling them that if you have a finite persistence time for this run-and-tumble particle, they didn't use the word run-and-tumble, but it's exactly the same process. Okay, so Mark Katz, he has a series of lectures in Schlumberger lectures. This was in 1974, and there are many works which unfortunately were completely ignored by these active literature people, because they were interested mostly in many-body collective effects, but it's interesting also at the single particle level. Okay, and so in this community, it's usually called the persistent random walk. This is the name which was given by Mark Katz. So for me, it's nice because this is the simplest, if you can think of simplest non-Markovian process. One of the simplest. I mean, random acceleration is still probably the simplest. Okay. So what is the run-and-tumble particle? I mean, so let me define very precisely here. So think of one single particle. I'll define in d dimension, but you can generally. So this picture is in 2 dimension. So this is actually, this is a motion which is exhibited by bacteria like E. coli. So what it does is that it starts, let's say, at the origin, and it chooses a direction at random, and then it just ballistically moves in that direction. Let's say first with a constant velocity v0, and so this is called the run. Okay, so at the end of the run, it tumbles, meaning that it reorients itself, and let's assume for the moment that is instantaneous tumbling, and then what it does after this, it chooses again one direction at random, and then moves again with the same speed v0 in that direction. Now this is the run, and this is the tumble. Okay? So it just goes ballistically like this, and then suddenly is jittery motion like this. Okay? So if you look at the trajectories, so they look like this, and so on. Now, so this run time, how long it runs in one direction, So this run time is a random variable. So it chooses to run up to certain time, tau. So this is the run time before tumbling. And this run time is chosen from a distribution. And if you say that this tumbling occurs at a constant rate gamma, then this is just exponential distribution because it doesn't. So basically, you write this as gamma tau normalized to 1, where this gamma inverse is a time scale, which is called the persistence time scale. So that means it persists in that direction with a mean time 1 over gamma. Okay. So if you are doing Monte Carlo simulation, so then the precise rules are the following. So in a small time interval dt, with probability gamma dt, so gamma is a constant, so gamma dt, you tumble basically. That means you change your direction and you move to a new direction. And with the complementary probability, 1 minus gamma dt, you just continue to move ballistically with speed v naught. This is the simplest model of run and tumble. So if you are in one dimension, it's very easy to see in one dimension. So one dimension, you just have a particle, it just goes in one direction, then it changes suddenly the direction, goes the opposite direction, then it goes in this direction. So if you plot the position of the particle, okay, so what's the equation of motion in 1D? It's very simple. So dx dt is just v0 into some sigma of t, and this sigma of t, it goes from -1 to +1. So it stays +1. So when it's +1, the particle is moving ballistically with v naught speed. And then it's, at a random exponentially distributed time, it changes direction, it becomes -1. Then it remains -1 for a while, then +1, and so on. So it's a telegraphic noise. And it's called active particle because for active particles, these guys move without even applying external force. It absorbs energy from the environment and just self-propels itself. Okay, and so this is a telegraphic noise. So and these intervals here are distributed by exponential distribution. Okay, so it moves and then it changes direction, then moves, changes direction, flips sign, and so on. Okay, and in the higher dimension version is that here it's only 2 state, but here it can choose continuously from any direction. It can move in that direction. Okay? And so this is, if you say this is like a Brownian motion, but with an effective noise, the difference is that this noise, if its mean is 0, this telegraphic noise, but if you compute its correlation function, so the correlation function is actually v0 square exponential -2 gamma t1 minus t2. Okay. So you see that there's a finite, it's not delta function for finite gamma. So that means there's a finite memory correlated, in time in the noise. Okay. And one thing you can check is that if you take, and if you write this as just multiply and divide by gamma, and then now if you take the limit, gamma goes to infinity, and v naught going to infinity, but keeping v0 square over gamma equal to 2d fixed. Then you see that this guy here, when gamma goes to infinity, this converges to a delta function. And then this is, if you fix this scaling ratio as 2d, then it converges to white noise. So only in this limit, when gamma goes to infinity, this active particle becomes a passive particle, passive Brownian motion. Okay? But with any finite gamma, it has a memory, the noise has a memory, that means x of t is clearly a non-Markovian process. Okay? So you need to know the previous noise, what happened in the history of sigma t. And so you can ask then, okay, so this is the model. And now the question I want to ask is the following. So you can ask, what happens in D equal to 1 about the first passage probability. So this has been studied in recent times. So first passage means again the same thing. That is, I want to write down, ask what's the probability that this position of the particle does not change sign up to some time t naught. Okay. So first passage properties of RTP has been studied. Again, there are many people in this room. I'll not. So we have some joint work with Abhishek and Anupam and others, Sanjeev, and also Artuso et al. So actually, there was first paper by George Weiss, goes back to 2002, and then in more recently, this Malakar et al., Chris, and then Ledusal, myself, Cher, and also Christian and his collaborators have studied. So many people have studied this problem in 1D. So 1D, again, you can write down the Fokker-Planck equation, but you just have to, the reason you can solve it because there are only two states. So you have to keep this additional, like for random acceleration process, we are going into the xv plane to make it Markovian. So here what you have to do is you have to define the survival probability S plus minus Tx naught. So S plus of Tx naught, that means what is the probability that the particle survives up to time t starting at x0 and starting with an initial state of sigma plus 1, that means initial velocity positive. And similarly, S minus is the survival probability starting with a negative velocity. And then it's quite easy to write down the explicit equation for, so I'll just write down the equation, I will not solve it. So let me see, I just don't make a mistake. Yeah. So this is just a V naught. So here I'm using a backward equation. I'm directly writing in terms of the initial position. So because it's easier, you can do it the forward way also. So this is valid in the domain x naught positive. Okay, you can see that these are the advection terms, and this is the rate in with which you are going away from one state to another state. So it's just a simple master equation that you can write down. Okay. Now the tricky thing here is the boundary condition again. So what's the boundary condition? So the boundary condition would be that the S minus at 0t should be equal to 0, because if you start at the origin with a negative speed, you will immediately cross the origin. However, if you start with a positive speed, you can still survive up to time t. So this is unspecified. Just exactly like in the random acceleration problem. Yep. This is unspecified, okay? And then you have the initial conditions, which is that the S minus at x naught at t equal to 0 is 1 for all x naught positive. So with this, you can actually solve this problem. I'll not go into the detail, but it's not too difficult to solve this problem. You can find in these papers. And so if I say survival probability starting at the origin, which is a simpler expression, and I just define this as S plus of t0 plus S minus of t0 with probability half. So I'm saying that initially, suppose I say that initial speed was plus with probability half and initial speed was minus with probability half, then this is just the survival probability up to time t. These things, yeah, because there is no explicit noise here, you see. I didn't put an extra thermal noise here. because this is just advection. See, if you have a dx ballistic motion, dx dt equal to v, okay? Then, when you write down the Fokker-Planck equation, you remember that normally Fokker-Planck equation, when you, let's say just think of this, just a Markov process. Dx dt equal to v plus white noise, right? This is the diffusion noise. So when you write down the Fokker-Planck equation, so the second derivative term comes from the thermal noise, this d here, okay? And then there's the first derivative term, which is Vp. This is a, because if you didn't have this term, you see this is just a current. So rho v is just a current basically. So this is just a continuity equation, okay? So the same reason you have just, this is just a part of the continuity equation basically. And here you don't have any external thermal noise. If you have, then you have just to put, second derivative term there, okay? Yeah, exactly. No, this is exactly Dirac type of problem, precisely. Yeah, this is precisely. This is, but this is interesting because if you look at the path integrals of this, it has not been explored too much. This will be exactly relativistic, Dirac path integrals as opposed to Schrodinger path integral, basically. Absolutely. No, this is wide open actually. I mean, nobody has really exploited the thing. I mean, everybody understands, yeah, there's a similarity to Dirac equation, but it has not been, fully exploited. That's a sort of interesting open problem. Okay, so if you do that, I'll just write down the final answer in 1D. So I'll just take 5 minutes more, and then. So these are Bessel functions of I variety. So Bessel functions, both I0 and I1, in general I in mu of z, for large argument, they go like e to the power z by square root of 2 pi z. So you see that, when you take large time limit, when time is much bigger than this gamma inverse, so, or if you alternatively, if you take gamma to be very large, for finite time t, when the argument goes very large, then it goes like exponential of gamma t by 2, which cancels this term. And essentially, so either when gamma t is much bigger than 1, this again goes like square root of t. So you get back the usual diffusive answer, okay? But then you have a, so if you plot this function as a function of time t, it decays. So this is s of t 0 versus t. It decays and, okay, this is the 1D result, solving by Fokker-Planck equation, okay? It does not depend on V0. It does not depend on V0. Survival probably does not depend on V0. Okay. We'll see that more later. Okay. So right. Now you can also, modify this basic model a little bit, where you can say that during each run, I draw the velocity speed from some distribution independently, W of V. Okay? So draw the run speed independently from WV after each tumble. So the problem that I was talking about so far now was just the delta function of V minus V0. But you could ask any distribution of the speed. It just has to be a positive support because V is speed, so it's positive. So I can ask, each time I just choose the speed from a distribution with positive support. And so you can ask this question also for what happens to the result for WV in general. Okay, so the question I want to address, and then I stop in a minute, is that now going beyond d equal to 1, if I'm in d dimension, so this is the d dimension, okay? So take a d-dimensional RTP, starting at the origin. So it's doing this motion, and So first think of just this WV equal to delta V minus V naught, or more generally of WV. And what I want to ask is the survival probability SD in D dimension up to time t. By survival probability, I mean what is the probability that the X component of the RTP stays positive, that is, does not cross the origin. So for the passive particle, you see this is a trivial quantity, because passive Brownian motion, if I take a d-dimensional Brownian motion, that means each component is doing individually Brownian motion, independently. So if you take a random walker in d dimension, that's equivalent to taking, it's just union of random walkers in 1 dimension, 2 dimension. Each component is doing independent random walkers. Okay. So therefore, if I ask this question for ordinary Brownian motion, it's trivial, because it doesn't depend on the other dimensions, so it will be just the 1D result. Okay. But for RTP, this is certainly not true, because these components, they are highly correlated. Okay. So for each run, the components are correlated, and then they are correlated from one run to another run. So it's a much more complicated. So the dimensional dependence, you would expect that it should be it should depend quite strongly on the dimension. Okay. And so what happens in higher dimension? We have seen that d equal to 1 was this answer. Okay. So what happens in higher dimension? And here I want to show the pictures. How do I? And there was a surprise, and after that I'll stop, and the next lecture I'll try to explain why we see this surprising result. Yep. Yes. Yes.
In different dimensions, we can also see the problem that way, like depending on the component of the velocity in that dimension.
You will see that. You can think of, but it's not so easy. Okay, because they are strongly correlated, these different components. Okay. So the question is clear, right? I'm in d dimension. I'm asking what's the probability that the X component stays positive up to time t, okay, of the RTP. So first thing, of course, what you would like to do is simulation, right? So you do the simulation. So this is the d equal to 1 result that I told you already. So this was the d result, and it works fine. Okay. So the line is a theory, and this is simulation results. Now we go to d equal to 2. Didn't change the curve. All t, at all time t, is exactly same answer. Now we go to d equal to 3. All time t, it's exactly same answer. So this is all and it's independent of v0 speed. So this was for a delta function, with this constant speed v0. So now I choose from a distribution w of v, very, exponential. So I choose from Cauchy distribution, which is this guy here. Look at this, exactly same, didn't change. Okay. At all time, it's not just universal at late time, it's universal at all time t. T equal to 0.0001, it's universal. Okay. So in the beginning, we thought there was a bug in the simulation, okay, and but then it turns out that it's not a bug. Okay, it's a very deep. Behind it, there's a very deep theorem, which is called the Sparr-Anderson theorem. Okay, but it's not so easy to see how you can apply this, because Sparr-Anderson theorem is for discrete time random walks, and it's not so easy to see how you can apply Sparr-Anderson theorem to this problem, to the RTP problem. But eventually you can do it, and you can prove that indeed this S of t is completely independent of D, it's completely independent of WV, and it's just this universal distribution is given by precisely this formula in all dimension, okay, and all W of V. Okay. So that's the result. So what I'll do next lecture, I want to show you this, how to prove this result. And I'll tell you also this about this power Anderson theorem, for which actually is very useful, but not many people know about it very well. And it's actually, I mean, it's a great theorem actually. So that would be basically the next lecture. So I'll stop here.
Questions?